Hi everyone, welcome back to my channel. This is Xiaofu, an enthusiastic researcher in dynamics, control, and vibration. In this series of lectures, I'm continuing to help you to design a controller from scratch. So in this lecture, we are going to have a short lecture this time to look at how we can use Caley Hamilton theorem to convert continuous time system to discrete time system. And in the next lecture, we are going to look at some of the important system properties, such as stability. If you like my channel, please subscribe to my channel. Thank you. So from the last lecture, we have looked at how we can deduce or come up with an expression for the system response, which we have done already. So that will be consisting of transient response plus steady-state response, which transient response is depending on its initial conditions. And steady-state response will mainly rely on its A and B matrix. So in the next lecture, as I mentioned, we are going to look at some of the other system properties. But one question we would like to ask, if there is any other use for the matrix exponential other than the one that we derive for the system response. Of course, it can also help us to approximating system behavior in discrete time. So let's look at a comparison between continuous time signal and also discrete time signal. Right, the blue curve, you can consider that as a continuous time signal. While discrete time, you will have to define what is your time step. Right, so right now you can see the right dot are those discrete time point. So the problem is that in between those discrete time point, how is your system going to evolve? You probably don't have much information or much idea. Sometimes, okay, we might think it might just be a linear line connect this one to another one, right? Or it can also be a zero order hold, which means remain constant and then jump when you get the next point information. So, but then how do we predict and evolve, right? So in this one, we are going to introduce zero order hold. Okay, as I just mentioned, okay, the sample signal doesn't provide any indication of what happens between sampling instants, right? So there are some of the challenges here is we need to predict the state at the next sampling instant or next sampling time point based on the only on the state and also the control signal at the current sampling instant, right? So then your sample time k will be a function of your time step times your time index, right? So your when you discretize your system, your time step is also very important. You don't want to use a very rough or not very fine time step. So here, as I just mentioned, okay, unlike state and outputs, control signal is basically well under our control. So we can guarantee what happens during sampling interval by regulating the control signal to remain constant over a sampling interval, right? So therefore, this is the one that I just mentioned. This is a zero order hold. As you can see, your control signal remain constant, and then all of a sudden in the next interval, it actually jump to a different value, right? So this is a zero order hold, which means within the time interval, your control signal remains constant, and it only changes when it reaches the next time step. So in the last lecture, we know, okay, so we have this matrix exponential, but to design a controller in discrete time, we would like to have the following type of expression. So instead of x of t, right now we use those discrete time sampling instance, x of k plus 1, which equals to a of d. D means discrete time A matrix times x of k. So it will be different from the continuous time A matrix, and plus b d times u of k. Those k are all current sampling instance. While as we mentioned, zero order hold, we hold constant control signal between sampling instance. So therefore, when we look at our continuous time expression, x of t equals to e to the power a times t times initial condition plus the rest of the term, which has the control signal u over 0. As we consider u is a constant, so u is no longer a function of time, so we can, especially within a time sample or time interval, that's what I mean. So then your u can come out of the integral as a standalone constant. And also, so after that, your x of k plus 1 depends on your current state and also your current control signal u, right? So then you have your entire expression. So right now, how your, let's say, discretized A matrix look like is actually a matrix exponential, right? So that's why it helps you to convert from continuous time system to discrete time system. Right now you saw it, right? So your t is your time step. Let's look at the continuous time system model. X dot t equals to ax plus bu. So it's a function of states and also control signal. So the forward Euler approximation is indeed here in this lecture will be the same as the zero order hold. So your next time state xk plus 1 equals to x of k plus t which is your time step times x dot k. So if you convert, if you look at x dot k, is a function as we just mentioned, x of t and u of t. But since we are going to discretize it, so it only depends on the current one, the current state, and also the current control input to predict the next one. So which is not very difficult if we just plug it in. So we get this expression. This I'm not going to elaborate more since it's not difficult to derive. It's very straightforward. So then if we look at our explanation and thinking about the one that I just mentioned, so convert your continuous time system to discrete time system. So we can use the zero order hold explanation. So which means we consider our input u or control signal u remains constant within a single time interval, right? So you can also call it forward Euler approximation. So here the most important one that I want to mention is this is one of the approach zero order hold that can help us to convert from continuous time system to discrete time system. And this is also very, very popular in most of the control system, and it's also very simple to achieve. As you can see, A of d, which is the can be considered as the exponential matrix, right? So that's why Caley Hamilton expression or theorem is very important to help us also to convert the continuous time system to discrete time system. So here, very easily, if you want to implement this in MATLAB, so you can simply use a C2D continuous to discrete time system, which is a MATLAB syntax or MATLAB built-in function by choosing the zero order hold approach, but you also have to define what is your time interval. If you go to MATLAB, I have a quarter car model, which I already list out everything. Let me run it. So I have continuous time state space representation and also discrete time state space representation. We can take a look. So let's say, so my continuous time is here. Let's check what is the A and B matrix. So if you can say your A matrix is a 4x4, as a quarter car model, you have 4 states. We can look at A matrix, and also let's look at the zero order hold one, which is our let's say discrete time, right? So here I define your time t, or interval is 0.1 second. Of course, you can define any time interval, but for simplicity, I will define 0.1. So let's take a look, and this is the built-in function. ZOH means zero order hold. If you look at it, so system discrete time, and you can see sample time 0.1 seconds, right? It also tells you it is discrete time state space model. And looking at your A matrix, it does become a different A matrix, right? So I also simulate these two together. So the discrete time, if the time interval wasn't so coarse, it should follow mostly of your continuous time system, but as you can see, it also have a lot of discrete time point to connecting together. This is just one of the quarter car state response. Yeah, that's it. That's everything for today. Introducing the Caley Hamilton to help you to convert from from continuous time system to discrete time system. And that's it. If you like my video, please feel free to subscribe. See you next video.